Welcome. This is just a quick update on natural spaces, natural metric spaces, natural groups and natural graphs. I want to wrap this up, and so this is kind of a way to get organized. So here are the definitions. We have seen that a metric space is natural if there exists exactly up to isomorphism 1 group structure on that space, which is compatible. And the corresponding group is then called a natural group, and a graph is natural if the geodesic metric which it defines is a natural metric space. So these are then kind of natural topological groups, so where the geometry determines the algebra. And I have made here a list of what I currently kind of know examples of spaces I know where things are natural, like the alternating groups, the symmetric groups, the cyclic groups. Most cyclic groups are natural. Only the Z4 is kind of on Z8 and Z12, etc. These are problems. So we have this structure of a billion groups, finite abelian groups, and so the only problem which we really have is this Z4, where there's a dihedral structure which is implemented too. Kind of the first non-abelian example of a non-natural group is Q8. Then we have the integers. That's how I started. The free groups, and more generally the free groups with n generators, is not natural. We can just produce, essentially we put the infinite dihedral group on one of the generators, and that produces another non-abelian group structure. So that's not natural. I've looked also at the Lamplighter group, which is a group, but a nice group. It's kind of generated by two generators. One is the translation R, right translation on the integers, and so L is you light the light at every you can light the light. When you light the light twice, then it turns it off. So you switch it on and off, and the generators are just lighting a light, going n steps, lighting that light, going n steps over, light, extinguishing this light and going back, extinguishing this light and coming back. So you make two tours, and in one tour you turn on the lights, in one tour you turn off the lights. This generates this group. So a general configuration is finitely many lights, and it's just essentially because it's the Rath product of Z2 with the integers that it's not natural. So there is the integers you can replace with a dihedral. You can build a non-abelian group structure. Interesting, kind of, if you take finite groups and you take the free product of finite groups, it's also something I've looked at. So here we have an example of the Cayley graph of the free group generated by Z2 and Z3. So that's known to be the modular group PSL2Z, so all 2 times 2 matrices with integer and interest determinant 1, modulo -1 and 1, which is kind of an interesting non-abelian group. It's known to be the free group of generated by 2 matrices. You can generate it by 2 matrices, and these 2 matrices don't produce any other relations. Also, for Lie groups, it's pretty clear. So if there is a B invariant metric, like for compact groups times Rn, it is natural. So that's essentially comes from the knowledge of Lie groups. There's any metric, which produces on a manifold, which is invariant, and the group translation must be by a theorem of Montgomery, Zippin, or Gleason, who was here, that it has to be a Lie group. So this is So there's no other possibility. I don't know whether the complement, if a Lie group is not of that form, so if it's compact times Rn, these are the ones which have B-invariant metric. Euclidean group, the group of in the plane, for example, doesn't have a B-invariant metric, and so it's not so clear whether it's natural or not. I don't know yet. I don't really know yet about the p-adic groups. What I know now is that the metric space coming from the p-adic group. So if you look at the p-adic groups, then there is a metric coming from the valuation, and this is producing a compact metric space, which is a Cantor set, and this is not natural. And the reason is what we looked at last time. There are group structures. This is in the case Z2, in the case CP, there are other group structures, non-abelian group structures, which preserve this metric. So it's not, these are not natural metric spaces, but it's not excluded that you can kind of find some other metric. I don't believe there is another metric which kind of can produce this thing. So I actually believe that these p-adic groups are not natural, but I don't know. Also the Gupta-Sidki or the Grigorchuk groups, I decided what happens there. So there are some general results which help a little bit. One of them is about, some of them are about graphs, some of them are about groups, some of them are about metric spaces. The products, essentially any product you can look at for graphs, like the Shannon product or the zigzag product, which is a kind of related to the semi-direct product of the groups. This Shannon product is related to the direct product of the groups. The free product is related to the free product of groups. And so I've also looked at the Lefschetz number. So every group translation produces a natural automorphism of the graph, and then you can look at what it induces on cohomology, and you can look at the supertrace, which is called the Lefschetz number generalizing the Euler characteristic. And if you average all these Lefschetz numbers, then you get one. That's what I proved once 9 years ago. So about finite groups, yeah, direct products, semi-direct products. The reason is finite groups essentially are just everything is determined by their Cayley graphs, and you can produce weighted Cayley graphs and take the Shannon product, the weighted Shannon product, or weighted zigzag product to actually get natural. So that's no problem also for the free product. I actually have a picture here of the free product of Z2 with Z3. So Z3 here and Z2. And so this is kind of, if you would continue that. And so this produces then the PSL, this PSL2Z. Yes, also the rest product appears here. That's kind of the Lamplighter group is really a prototype, kind of illustrating the rest product, because it's just C2 crowns product with Z. But it's a semi-direct product of an infinite group Z2 to the Z. This is a countable group, not like Z2 here. Z2, these are uncountable, these are Cantor sets. Also about completions, for example, Q. You know, if you take Q, for example, here, that's natural. So you can take Q. The rational numbers is natural because if it would not be natural, then also the reals would not be natural. Oh, I'm not yet sure about the profinite limits, whether this preserves naturalness. But there are still open questions to ponder. But I decided to essentially wrap it up now and move to some other projects which I've neglected. Cool, that's it for today.